So welcome back, everybody, and welcome to this session before the break. So today we are going to discuss further the algorithm and the implementation of the quantum Fourier transform and how this actually links to potential topics for the second project, and also the quantum phase estimation algorithm, which has been a central algorithm, for instance, for calculating the energies of a Hamiltonian, or as a basic building block in Shor's algorithm. And we will come back to possible themes for the second project at the end of the slides here. So as I wrote in the email, the slides this week are different from the Jupyter notebook. And that is simply because I haven't been able to include the quantum circuits into a Jupyter notebook. So this is just me blundering with some technicalities. So the content is different. And in the Jupyter notebook, as you can see on the link here, there we actually implement the quantum Fourier transform, and we implement the quantum phase estimation algorithm on the matrix which you had in project one, the simple 4x4 matrix, which is a 2-qubit system. So that's an exploration. So there are fundamental connections between quantum Fourier transforms, the quantum phase estimation algorithm. There's a connection to Hamiltonian simulations if you're dealing with an analog quantum computer. There's a connection to the variational quantum eigensolver. And then we're going to discuss these themes for the second project. So if you look at the quantum Fourier transform, where it pops up, you can think of that as a kitchen ingredient. It's a basic building block in many of the quantum algorithms, which we will talk about later. So Shor's factoring algorithm, it's essential. It enters there in order finding, period finding, the quantum phase estimation, which we will discuss later today. And then we also have several quantum simulations algorithms. So how many of you have heard of this HHL algorithm? This is a famous algorithm for solving linear algebra problems. Now, I'm going to take off the recording temporarily because I'm going to say something which is not proper scientific practice. So we have the HHH algorithm, which plays an important role in solving linear algebra problems. Now, I know that some of you are interested in solving differential equations. So if you think of the diffusion equation is an equation in both 1 and 2 dimensions, which you can rewrite as a plain linear algebra problem where you have a matrix A times an unknown vector X equal to a known vector B. And this is essentially what this algorithm does. Now, this algorithm is also very interesting because it uses the QPE, it uses a quantum Fourier transform. But for those of you who are interested in many-body physics, this algorithm links well with Green's function theory and also an algorithm like time-dependent Hartree-Fock theory. And I know that there are some of you who are also taking another course, which is called Computational Physics 2, where some people may be interested in studying the time-dependent Hartree-Fock. So this is a possibility to catch 2 birds with a stone, where the second project here could actually be an exploration of the HH algorithm with a link to time-dependent Hartree-Fock theory, and then also develop a plain time-dependent Hartree-Fock theory algorithm in the other course. And then one can actually merge the 2 projects. So that's a possibility. There is another algorithm which we will discuss after the break, which is called the quantum approximation optimization algorithm. And so the QAOA algorithm is actually also a very important algorithm in quantum computing. And it has been widely used in optimization problems. And I know that some of you are interested in financial optimization problems. And this QAOA algorithm, the quantum approximation optimization algorithm, is something which we also will discuss after the break. So this is another example of a variational quantum circuit. So it follows this basic philosophy, which we've been having about variational quantum eigensolvers and parameterized quantum algorithms. So I'm going to say a little bit more about these possible projects at the end of the lecture, so that you can use the time during the break to figure out what you would like to do. So I'm going to come with proposals for the projects, but I know that many of you are already interested in some specific variants. So take some of your time and use the break to, in case you have something specific you want to study. Else, I'm going to propose several projects, and you will see a list of topics at the end of the slides for this week. Okay, so this is a little bit about the importance of quantum Fourier transforms. So it's a basic ingredient. Now, another thing which we are going to show today is the count of algebraic or floating point operations. And the counting is a dramatic increase in computational speed up compared to fast Fourier transforms. So this is something which we will also discuss today. So let's quickly remind ourselves what we had last time. So what we discussed last time was the link between the discrete Fourier transform, which is something which you can write as a matrix. So this Fn is called the discrete Fourier transform matrix. So this is the discrete variant of the continuous Fourier transform. And if you just write this out in its brute force way, so you would have this matrix acting on an initial vector, which then could be these vectors xj's, where these xj's can take different values. So these are all complex numbers. And when we write it out, this is something you can simply write out in terms of a matrix times a vector. Now, every element here, as you can see from the exponential with 2 pi times I, are complex numbers. So that means that you're doing multiplications of matrices with vectors involving matrix vector multiplications with complex numbers. So there will be multiplications and also additions. So these are the typical operations, the floating point operations, which you end up. So that's the discrete Fourier transform. And then what we did was actually to take essentially the same expression, but then we replaced the same machinery. So you can actually rewrite the quantum Fourier transform like a discrete Fourier transform. There is nothing which hinders you doing that, but then you will not be exploiting the possibilities which a quantum computer gives you. So mathematically, the expression is the same, except that now this K is a set of bits which we're acting on that, and this is a specific state. So the QFT maps the computational basis state to a coherent superposition of all basis states with phases which are determined by the values X which you have from the very beginning. So, and this map is linear. And so for a general state, you would then have some mapping where the mapping is now given by this QFT transformation acting on the state. And this has some coefficients, and then it has this QFT operation here. And this is the thing which we are going to look at in more detail today. And we are going to look at how we set up the circuits. And in the Jupyter Notebook, you will find an implementation of this. So one of the alternatives for project number 2 is to implement the quantum Fourier transform on a quantum computer, and also you running this on your laptop, classically, but with a quantum algorithm and the quantum phase estimation algorithm, and then extract the eigenvalues and compare with what you got from the variational quantum eigensolver from project 1. So this is a pretty well-defined path for project number 2. So that's one of the many alternatives which we have. Anyway, what I'm going to do now is to quickly dive into the Jupyter Notebook, no, the whiteboard, sorry. And we are going to look at the case where n here is equal to 4. That means that we have 2 qubits. So when we are looking at a standard Fourier transform, a discrete Fourier transform, n would then just be the number of states which we are transforming. But now this is given in terms of the number of qubits with a base of 2. So this is the total number of computational basis states which we can have. And in order to understand the algorithm, it's actually best to look at the case when we have 2 qubits, because it's easy to see how we can generalize from that to the general algorithm. Okay? So let's switch to the whiteboard and then come back to the slides, because when it comes to the QPE, I'm going to use the QPE, the slides here, to demonstrate and to develop the quantum phase estimation algorithm. Okay, so let's switch back to the whiteboard and look at the derivation of the quantum Fourier transform. So if we look at the discrete Fourier transform, let me just do a counting of the number of floating point operations before we switch to the quantum Fourier transform. So the discrete Fourier transform, DFT, when we do the counting, what it has, since it's a matrix times a vector, it has n squared complex multiplications. So when we are looking at the number of floating point operations, multiplications, and since we are multiplying a matrix with a vector, there are also going to be n times n minus 1 complex additions. So keep in mind that the numbers are complex. So a complex addition is actually 2 real floating point additions. A complex multiplication, on the other hand, is 6 to 8 real multiplications. So when you operate with complex variables, you're obviously penalized because you have more operations. But if we look at this, if we sum this together, you see now that the algorithm has typically the number of floating point operations, which is proportional to n squared. Okay? This is the roughly the number of floating point operations, and then obviously this is multiplied with a constant. So if you compare with the real floating point multiplications, you have to multiply this number with a factor of 6 to 8. And you have to multiply this number with a factor of 2. But what you have is just some constant alpha times n squared. So n squared is a dominating number here, okay? Now, then, this algorithm has been replaced since the 60s with something which is called a fast Fourier transform. And there is a reason for why that has replaced the standard brute force discrete Fourier transform, because this one has n times log 2 of n complex multiplications. So it's actually 1/2 complex multiplications. And it has, in addition, something like n of log 2n complex additions. So what we say then is that the number of floating point operations is now roughly something which runs like O of n of log 2 of n. So this is the expense of the fast Fourier transform. And you see that this is clearly an improvement compared with the brute force direct Fourier transform, okay? Now, what we are going to show later today is actually that the quantum Fourier transform has a number of flops, which goes like O of n squared. And n is the number of qubits. So one of the reasons why I repeat some of these things is that n, which we have here, the number of states. So if you have 2 qubits, this corresponds obviously to 0, 0, 0, 1, 1, 0, and 1, 1. But this is given by 2 to the power of n. Okay? So this is a dramatic reduction of the number of floating point operations. To see that, suppose that you have one of the existing quantum computers nowadays, which has between 50 and 100 logical qubits. That means that the DFT, the direct Fourier transform, has O of 2 to the power of 200, which is roughly 10 to the 30th. Okay? If you do 200, this is 2 to the power of 10 to the power of 60. And by 2030, we are going to have quantum computers with 1,000 logical qubits. Then this number becomes 10 to the power of 300. Okay? So if you then look at the fast Fourier transform, and you plug in the same numbers, this is going to be given by, so that should be 1 DFT, sorry. Yeah, so right. So this is going to be roughly 100, or rather 2 to the power of n times, so we have an O of n of log 2 of n. So, and if you plug it in, that's going to be 2 to the power of n, and then we're going to have n, and then log 2 of 2, which is 1. So this is proportional to n times 2 to the power of n. So 2 to the power of 100 is actually 10. No, wait, sorry. 2 to the power of 200, I'm actually messed up a little bit. This is proportional to 60. 2 to the power of 100 is actually, this is 100 times 10 to the power of 30. Sorry. Okay. And then we add the QFT. And then we have the number of floating point operation, which is n cubed, n squared, which is then 10 to the power of 4. So it's a dramatic reduction in the number of floating point operation. So if you then look more into the future, 3-4 years, so like Fujitsu has claimed that they are going to have 1,000 qubit quantum computer. IBM, many of the other companies have actually claimed the same. So if you have 1,000, then you have 2 to the power of 2,000 for the discrete Fourier transform. You have 2 to the power of 1,000 for the fast Fourier transform, which translates into 10 to the 301, to the power of 301. And if you then do the standard QFT, then it's just 10 to the power of 6 floating point operations. So if you now think of the quantum Fourier transform as a kitchen ingredient in quantum algorithms, you see that there is a dramatic speed up. So during the lecture today, we're actually going to look at how this count of floating point operations, why we get n squared actually. Okay, yep.
How many qubits would we need before it's beneficial to use a quantum computer instead of a fast?
Well, I would say even today with if you look at these numbers, if you're looking at 10 to the 30 floating point operations, and if you have access to let's say a petaflop machine, where you do 10 to the 15th operations per second, ideally, then you have 10 to the 30th. So you would need something like 10 to the 15th seconds to run that operation. So even with that, with today's machines, you would actually have, you would need to perform this operation here with roughly something like 10 to the 15 seconds. And you should compare that to the lifetime of the universe, which is estimated to 10 to the 17th seconds. So this is one of the quantum advantage benefits. Yeah.
Do we manage to implement multiplier transform on a quantum computer in that?
No, not yet. So because you still have lots of noise. So that means that the quantum, if you look at the length of these circuits, you will see that you will need actually a lot of rotation gates and Hadamard gates. And that clearly, with the decoherence which you have in standard quantum computers nowadays, there's a clear limitation to how efficiently you can implement this. But if you think just of the plain promise which comes from the quantum Fourier transform, then this is clearly a superior method compared to the classical ones. So the standard algorithm, which is used in basically all calculations nowadays, is the fast Fourier transform. And that is reckoned as one of the top 10 algorithms from the previous century and still in this century here. Okay. So what we're going to do now is to look at the QFT. Yeah. Yeah.
Do you think it's feasible that if we fix the decoherence signals,
yeah,
every single algorithm or computer running the fast Fourier transform will be swapped with the quantum version?
I would think so, yeah. Yeah. But nowadays, I mean, the calculations typically now have been done with just some few tens of qubits. And then the fast Fourier transform is still the algorithm which you would choose. But clearly, if you have access to a 100 qubit machine with 100 logical qubits, and you have noise corrections and error corrections algorithms properly working, then clearly the QFT should be superior to the standard fast Fourier transform. And you know, fast Fourier transforms are essential if you're dealing with signal processing, if you're looking at solutions of differential equations, etc., etc. So it's a basic building block in many, many algorithms in modern science, the fast Fourier transform. Okay, so what I want to do now is simply to discuss a little bit the derivation of the quantum Fourier transform. We did it last time, but now what we didn't do last time was actually to set up the circuits so that we can actually implement it on a classical computer or on a quantum computer. So let's look at these details. So we're going to look at this by starting with the 2-qubit quantum Fourier transform, and we're going to do that step by step. Okay? So let's just remind ourselves about the QFT. So what we have this is the number of configuration of 2 to the power of n, where little n is the number of qubits. So this acts on a computational basis. So we have a QFT, and I'm going to put a subscript n to indicate that this is for n basis states. So remember now that when we have n equal to 2, then we have 4 basis states, and the computational basis which we have is going to be given by these states here, 1, 0, 0, 1, and 1, 1. So this is the example which we are going to build now. And that means that when you look at this state x, which we have here, you could think of x as being one of these basis states. And then we transform one of these basis states, and we get a superposition of states. So the equation which we have been looking at is 1 over square root of n, and then we have a sum over k equals 0. And these are the basis states which we are acting on. And we have n minus n such states. And we have this omega of n of xk here, of k. And this omega n is equal to e to the 2 pi over I divided by n. What you see here, there is no difference here between a classical discrete Fourier transform and the quantum Fourier transform. So mathematically, these are just equivalent equations. What we have, however, if you think of this state, x, if we now encode this in a bit representation. So last week, one of the things which we did was to encode this as integers, but then due to the factor which we have in here in the exponential, we change to the floating point binary representation. But if we take the integer representation, what we have then would be something like xn of 2 to the power of n minus 1 plus xn minus 2 of 2 to the power of n minus 2, etc. And all the way down to x1 times 2 plus x0 times 2 to the power of 0. And what we have then is a state x, which is given by these qubits, xn minus 1 down to x0. Alternatively, we could write it like x0, x1, up to xn minus 1. And the x's, which we have, this x, they take only two values. They are either 0 or 1. Okay? So this is basically what we set up last week. And we started last week with the integer binary representation. That means that the state x here, depending on the values of these x's, we can then translate this into just one integer number. So that means that the state like 0, 0, if we plug that in here for 2 qubits, that means that this state would be state 0. 0, 1 would be state 1, etc. Now, one of the things which is important now is that this ordering here plays a role. And you will see that when we set up the quantum Fourier transform, this order, when we have performed the operations, is going to be swapped. So that means that we are going to get x0 as an output first, and then x1, x2, etc. So in case you want to have the original order you had, so where you would think of this as the most important bit, and then the second next important one, and that this one becomes the least important. Alternatively, you can just change it. I mean, this is up to you, right? I mean, this is just an ordering which we are choosing. And the ordering you choose is actually, in a sense, irrelevant. But the problem when we do the quantum Fourier transform is that the ordering of this most significant, second most significant, etc., is interchanged. And that leads to the introduction at the end of a swap gate. However, if you can keep track of these interchanges classically, which many people do, you can avoid having the swap gate. And this is done in basically most algorithms because a swap gate requires additional operations. So, but let's look at these details by taking the 2-qubit case, okay? So we are going to specialize there, and then hopefully you will see what the circuit is going to look like. So we are going to have bits x1 and x0. So these xi's, they can take values only 0 and 1, okay? As we discussed last week. And then we can, if we now take a binary float representation, and the whole thing is that what we want to do is actually to write this one in a compact way, okay? Because you see you have a 2 divided by n here, and you could obviously keep that one and encode things as integers, but you will see then that when you encode them as binary floats, it's actually something which gives rise to a more compact equation. So if we then look at that for the binary floats, then we have the binary float representation. If we now take x1, x0, that is going to be given by x1 divided by 2 plus x0 divided by 4. Okay? This is the way you would start with the most important. So you would think of this as the most significant bit. So this is just an ordering. I could actually swap this ordering. Okay? So whether you have AB or BA, doesn't matter. Most significant bit. And this one is the least significant one. So in general, the general equation, if you now have xm and xm minus 1, and this goes all the way down to x0, this is something which you would write as xm divided by 2 plus xm minus 1 divided by 2 to the power of 2, and then plus x0 divided by 2 to the power of m plus 1. And you see the least significant one is normally the last digit in a decimal representation. So these binary fractions which you see here, they will appear naturally in the tensor products which we get when we set up the QFT. So let's continue a little bit. And in our case, when we look at this state, when we go back to the integer representation, then we have x1, x0. And then we know that this x, the number which we have, is actually 2x1 plus x0. This is for integer binaries, okay? So for 2 qubits, if we now set up the QFT, and I'm going to put n equal to 4, acting on a state x, this is simply going to be given by 1 divided by 2, and then I have k equals 0 to 3, and then e to the 2 pi ix of k divided by 4. Now, sorry, not k, but divided by 4, which is now n, uppercase letter n, multiplied with k. So since k1 and k0, so we will also have that k is now given by 2k1 plus k0, and k1, the basis which we have, are also states which now can only take values which are 0 and 1. So then if I write out this Fourier transform, this quantum Fourier transform N4 on x1, x0, this is simply 1 divided by 2, and now the sums of k1 and k0. So I can replace these exponentials with a product. You know that when you have a sum there, you can simply replace this one with a sum over values 0 and 1. So I have e to the 2 pi I of 2x1 plus x0, and then I have 2k1 plus k0. So it should be a plus here. Let me be a little bit more careful with the signs. Plus k0, these are the values, and divided by 4, multiplied with k1 and k0. So then what I do is to expand the exponent. So if you look at the exponent which we have here, and keep in mind, so let's just wait a little bit so people have time to write down. So if you then expand the exponent and use the fact that you have 2 pi times I of x1 of k1 is equal to 1 for integers. So these are integers now, keep that in mind, x1 times k1. Because if k1 is 1 and x1 is 1, this is 1. If k1 or kx1 are either 0, 1 or 0, then it's 0. And then you simply have exponential 0, and that gives us 1. So that means that what we get then, if you look at this formula of 2 pi of I times xk divided by 4 is equal to e of 2 pi I. And then I have x1 k0 divided by 2 plus x1 of k1 divided by 2 plus x0 of k0 divided by 4. And if we then look at this in more detail, if we take a look at this e to the 2 pi I of xk divided by 4, this is then equal to e of 2 pi I of K1. So we isolate K1. We have X0 divided by 2 and multiplied. So multiplied with E of 2 pi I of K0 of X1 divided by 2 plus X0 divided by 4. So then I can rewrite this operation, this QFT of 4, with 4 states, X1, X0. So these are the initial states which we're looking at. And we have 1/2. And then we are summing over K1 and K0, which can be either 0, 1. And then I have E to the 2 pi I. And now you see that when I take this K1, I can write that as 0, X0. Because that is the binary representation with float numbers of X0. Okay? So if you go back to the representation which you have here, if you just have X0, that is X0 divided by 2. And then you see that the next term is nothing but multiplied with. So let's wait a little bit so people have been able to write it. So the next term is E to the 2 pi I of K0 of 0, X1, X0. And this is multiplied with K0, K1 and K0. So when you now sum over the K1 and K0, which can be 0 or 1, then things are going to simplify because now K0 can be 0 and 1, and K1 can be 0 and 1. So if we do that, then it's pretty straightforward to see that this is going to be equal to 1 over the square root of 2. And then I have 0 plus E of 2 pi I, 0, X0, times 1. And then there's a tensor product with 1 over square root of 2 of 0 plus E of 2 pi I of 0. And then I have X1, X0 multiplied with 1. Now pay attention to one thing here. If you look at these expressions which we are putting up, this guy here, we have K0, which is the least significant qubit. But now we have the most significant here and the least significant here. In the previous equation, we have the least significant K1, if you're thinking of that as the least significant. But this is acted upon, no, this is the most significant, sorry, the most significant, and this is the least significant. So there is a reversing in order here. So the original state is most significant bit, least significant. But here we see that the most significant, if we keep that order, X1, X0, and this is also the way we are setting up this one, most significant, least significant. You see now that the actions here are swapped. So let's come back to this a little bit later. But this is the state which we then can generalize to a many-qubit state. And what we have found here is that the first factor, so just let us pay attention to this. So key point here, first factor depends only on X0, which is the least important. The second factor depends on X1 and X0. So the least significant phase actually appears first. And this is why the circuit output is naturally in a reversed order. So you can keep track of this reversed order classically, or alternatively, you can implement a swap gate. But any such gate brings in additional operations in a quantum computer. So let's continue a little bit with these small manipulations here. So it's useful now to remember some of the gates which are going to be playing a major role here. So if you think back of the Hadamard gate, we know that that one, when that acts on a qubit 0, it gives us the linear superposition. And similarly, if I have H acting on qubit 1, this gives me 0 minus 1 divided by the square root of 2. And then we have so this is the Hadamard. Just a quick reminder, because that is 1 over square root of 2, 1, 1, 1, minus 1. And then we have the phase, or the controlled phase gate. So this is a typically R2 here, which we have in this specific case. And that is given by 1, 0, 0. And then we have e to the power of 2 pi I divided by 2 squared, which is nothing but 1, 0, 0 of e of I of pi half. So for 2 qubits, this QFT, the quantum Fourier transform, is going to use one Hadamard on each qubit, as you will see later, and then one controlled R2 and one final swap. So we're going to set that up now. So let me just set up the kind of gate and the operations which we get. So the circuit which you would implement, and after the break, we're going to derive this circuit by just looking at the expressions we get so that you see clearly why the circuit looks like as it does, okay? So it's not something which you see immediately from this equation. So let me just state the way the circuit looks like. And instead of having qubit 0 here, typically, or x0, we say now that this is the most important or the most significant bit. So we would then have a Hadamard acting on that one. Then there is a controlled rotation gate, which is an R2 here, which is that the expression we put up on the previous whiteboard. There's going to be a new Hadamard here. And finally, so this is a controlled phase gate. And then finally, we have a swap gate. But the swap gate, as I said, as long as you keep track of this specific order, is often ignored in standard algorithms. But I have implemented it in the codes which you find in the Jupyter notebook. So this is the swap gate. And I'm not going to set it up now, but it swaps. If you act on the swap with 0, 1, it changes that to 1, 0. And if I do that on 1, 0, it changes that to 0, 1. If it acts on 1, 1, it just gives us 1, 1. And same with 0, 0. So it doesn't change 0, 0 and 1, 1, but it changes 0, 1 and 1, 0. So after the break, I'm going to bring back the equation which you see here so that you see more clearly how we actually get this specific circuit here, okay? And this is what you would implement if you are going to implement the quantum Fourier transform. This is, by the way, also discussed in Hunt's book in chapters 6.1 to 6.4. There is a pretty thorough description of the quantum Fourier transform. Okay, should we take a small break? Is that okay with everybody? Okay, so let's now look at this equation which we have here, this one, and then do it step by step and see how we get this kind of reversed order of the qubits. And then hopefully then you will see how this specific quantum circuit, which we put up here, why it looks like this. So let's take the first step. step 1. That is apply the Hadamard to the first qubit. So we start with the state x1, x0. Okay? This is our initial state. That's the one we are transforming now. So that means that if I do that, if I apply the Hadamard, x1, x0 on the first qubit, this goes over to 1 over square root of 2. And then I have 0 plus e of I pi. What is going on here? So it's not showing. Yeah, I'm actually writing. Okay, let me try. Let me start it again, because guys, you were not seeing what I was writing. So let me share again. Okay, this is what I wrote here. Thanks for pointing that out. So the first step, I'm going to apply the h to the first qubit. So we start with the initial state, x1, x0. These are the two qubits where x1 is the most significant one and x0 is the least significant. And you can always reverse x0, x1. I mean, how you label them, it's up to you. So when you do this operation, what you get then is I times pi I x1. And then we have a state 1 here. So this reacting on the first qubit and tensor product with x0. Now, what we know is that this e of I of pi times x1, that is always equal to -1 to the power of x1. So that means that what we have there is something which I can rewrite as 1 over square root of 2, and then I have 0 plus e of 2 pi I x1 divided by 2, acting on 1, and tensor product with x0. That was the first step, when we are applying the Hadamard on the first qubit. Then what we have is the second step, step 2, and then we have a controlled phase, which we label as an R2. So this adds a phase which is e of I of pi divided by 2, which is the same as I, only when both qubits are in the state 1. That means that if we look at this amplitude of 1 tensor product with x0, that picks up an extra factor which is e to the 2 pi I x0 divided by 4. So that means that that state becomes, when we have acted with that control gate, it becomes equal to 0 plus e of 2 pi I. And then I have, so this is with the Hadamard and the R2 gate. Hadamard and R2. Okay, so I have x1 divided by 2 plus x0 divided by 4, acting on 1, and then tensor product with x0, which is the least significant. Now, this is something which I then can rewrite in this binary float representation. So this state which we have here, this is equal to 1 over square root of 2 qubit 0 plus e of 2 pi I, and then I have 0 x1 x0 multiplied with 1 tensor product with the least significant qubit. Obviously, if I interchanged x0 and x1, I would have x1 there, and then just replace that with x0. Now, if I apply Hadamard, apply H to the second qubit, what we get then, if I do that, this just transforms into 1 over square root of 2 and 0 plus e of 2 pi I x0 divided by 2 multiplied with 1. So that's just one qubit, okay? So this is how that transforms, the x0. So what happens then is that in total then, hence the full state, when I take the tensor product, full state, not states, but state, is or becomes 1 over square root of 2, and then I have 0 plus e of 2 pi I, 0, x1, x0 multiplied with 1, tensor product with 1 over square root of 2, and then I have 0 plus e of 2 pi I, 0, and x0 with 1. So what we have, let me single this out now. So this one here is Hadamard plus R2 on first qubit. And this one is Hadamard on second. And so what the circuit has produced is the correct quantum Fourier transform, but with the qubits now in reversed order. So the qubits, when you look at this expression, is that the qubits are in reversed order, So what we need then, we need a swap gate to bring back in the order which we prefer, which we want to have, bring back from what we will get as a K1, K0. This is what we want. So because we are going to get K0 and K1. So that restores the conventional most significant to the least significant ordering. So this is typically the way you would set up. So the first qubit which you look at, you think of that as the most significant one. Then you have the second one. So this is just an ordering you choose because you're using this binary way to represent the binary float in order to represent the states here. So if you take the general product, you can then, and we are going to see that in the slides quite quickly. So each qubit then, when we look at the expressions, so if we look at the phases, let me just add this, the phases in the qubit, in this case in the 2 qubit case, they are 0 with x0, which is the same as x0 divided by 2, and 0, and then x1, x0, which is then x1 divided by 2 plus x0 divided by 4. And this can then move on if we add more qubits. So each output qubit stores a phase that depends on a progressively longer suffix of the input string. So if you have the 3 qubits, you would then have x2, x1, x0, and that would be x2 divided by 2 plus x1 divided by 4 plus x0 divided by 8. So as I said, there is nothing which hinders you to put x0 as the most significant one. This is just an ordering which I've chosen here. So I have, that means that when I set up a state, I have a state x2, x1, x0, instead of instead of x0, x1, x2. So this is an ordering which you choose. And each qubit, as you see here, qubit stores a phase that depends on what you might call a progressively longer suffix of the input string. So like this one here. So if you have many qubits, obviously the string becomes longer and longer. Now, the reason why I'm bringing this up is that the quantum phase estimation algorithm relies on us representing a real number in terms of a binary representation. So if your number is represented exactly, suppose the eigenvalue of a problem is going to be represented exactly by a binary float, then the quantum phase estimation algorithm should be able to find the exact energy. But we know that a number of bits is finite, which means that you cannot represent correctly every decimal number. So like 1 divided by 10, 0.1, cannot be represented exactly with a finite number of bits. Okay, so this is something which I'm just bringing up now because we are going to discuss the quantum phase estimation algorithm. Yeah. Oh, no, this is just an ordering which you choose, right? So because when you're setting up the algorithm now, you simply decide the order here. And that order which you see in this figure here defines the sequence of these operations. And the way you have ordered the system is the way you actually initialize the system. And this one, you can choose x0, x1, x2, etc. But you have to choose an order. And that's it, yeah. No. There's nothing magic with that. Except that when you look at bit strings, if you think of that, I mean, clearly the first one is the most significant one. And we use this algorithm, if you then go back to the, when we are encoding the information of, let's say, a 2-qubit state in terms of these bits like x1, x0, you would then use integers to actually set up this number x here, which is one of the possible state, 0, 0, 0, 1, 1, 0, 1, 1. So what we are going to look at now is the next step and why this quantum phase, the quantum Fourier transformation, how that actually appears in the quantum phase estimation algorithm. So what I'm going to do now is to set up things through the slides. So I'm going to switch from the whiteboard to more general cases. So let's do that. Let's change, and I'm going to stay with the slides for the rest of the lecture here. So let's let me find the slides. Here we are. So let's just blow up the screen. So what we have is this equation here. We did this rewrite in terms of binary fractions. I actually added here in the slides some step-by-step derivation of the product form. So if you want to look it up, I mean, but this is something which you probably are familiar with. This is an intermediate step, which I didn't set up when I did the 2-qubit case, because the 2-qubit case is a little bit simpler. But you can then see how you get this specific tensor product form, because what you have when you do the operations here, your state K, it contains this K1, K2, etc. And these are states then which can take the value 0 and 1. This K is something you would rewrite like this. And you know that when you have this exponential here, both X and K, where this X is just written like this formula. So this is what you have in here, X times K divided by 2n. You can rewrite this K now in terms of this formula, which is the one which takes the integer representation of a state. And then you know that this exponential, which you have here, and which pops up here, since the values K here are just written by a sum, this is something you can rewrite as a product. And when you have that, since this kn values just takes values between 0 and 1, then you can actually rewrite the quantum Fourier transform as this tensor product. And what we did afterwards was simply to manipulate these different exponentials here in terms of a binary float representation. And then we have this specific representation, which you see here, where we started with the least significant qubit, and then we end up this one with the most significant one, which is x1. Okay, so this is just essentially the generalization of that equation, which we obtained for 2 qubits. And the standard product, so the qubit, as we saw for the 2 qubit case, we can have a Hadamard gates, controlled phase rotations, and a final qubit reversal using swap gates. And this is just a repeat of what we did. The first output qubit in the product contains this phase here, and this is produced by a Hadamard on the first qubit, which generates this state. Then a sequence of controlled phase gates from the later qubits, adding the binary fraction phase. And this pattern repeats recursively for the remaining qubits. So this is the way you would build a QFT circuit by qubit by qubit. And here we have the 2 qubit case. This is the one we discussed on the whiteboard. And as I said, in many algorithms, you just keep track of this ordering classically, so you don't include the swap gate. For n equal 3, then what you would have is that the first qubit requires phase contributions corresponding to x2 plus x3 divided by 4. So this is the first qubit, and then the first qubit contains this factor, and this is exactly what the controlled R2 and R3 gates generate. So that means that for this system here, you would have a Hadamard, and then you do an R2, and then a controlled R3. Then you have a new Hadamard on the second qubit, then a controlled one on the second qubit here, and then a final Hadamard on the last one. And then you do a final reversal. So this is typically the way you would build up the quantum Fourier transform. So if you think of the general circuit, if you count from the top, you apply a Hadamard gate, and for each later qubit, k larger than j, for this is just a loop which you would have, you apply a controlled gate, and then you continue recursively with the Hadamard and the controlled gate, and at the end you reverse the qubit with swap gates. So the general phase is actually controlled phases, Hadamard, controlled phases, Hadamard, controlled phases, etc. So a general gate, when I use this quanti case set, if you haven't used this one, I actually wanted to bring up the name here in case you haven't used it. That's actually a very nice way by which you can set up circuits. So one thing I recommend, if you're a little bit, when you're writing, in particular for the second report, you know that you have access to all the source files, which I used to generate the lectures. So let me quickly remind you of that in case you have forgotten it. Yeah.
Spoken about adding more gates.
Yeah.
Is generally a bad thing. But do we have a way of diagnosing how much worse the algorithm becomes? Error or computation? I just need your gate.
Yeah. So this is something as when it comes to both noise and error corrections, this is actually the topic for another course actually. So I will not discuss that in this course, unfortunately. So there is a limit to how much I wanted to squeeze in here, but that is a topic by itself, which I would say error corrections would be the topic for an own 10 credit course. That's at least my feeling. Yeah, because there are several algorithms. So I would say I'm not going to discuss that in this course, unfortunately. By the way, if you have not, just as a small digression here, if you have not used these algorithms, so let me just find an example here. So if you go into the to the GitHub address for the course, you will find examples for every week. So if you go to source and you take this week, which is the 10th week, and you go into, because now I'm generating a distinct Jupyter notebook and a distinct PDF because I had problems with including quanti case set. But if you go in here, you will find week 10 TESH, and that contains these examples, which are, or the codes which I've used to generate these figures. So feel free to use this as you want, in particular when you're writing, let's say, the next project, because then probably you will have to write many, many different circuits. And it's a little bit boring actually to do this. Actually, some of these you can do with the ChatGPT. So ChatGPT is excellent on text. It still produces some kind of strange circuits, so you have to be careful when you set them up. But it's doing a pretty good job. When it comes to coding, I normally recommend Claude Code. So many of the codes which you see are actually codes which I have improved, because previously my plots were not that nice and illustrative. So you can actually grind through your former Python code and almost write, make me some nice plots. Well, it's not as simple as that, but it's a very useful tool. And I recommend using these. It makes life much easier. Anyway, so you can find all the source files which are used to generate Jupyter notebooks and lecture notes in the different weeks here. So let's go back to the slides for this week. And I always have to figure out where I left it. Here we are. And let's do a full screen. So the typical pattern which you find would be something like this. And this is just a schematic pattern rather than a fully expanded. The key point is the nested structure of Hadamard's and control phase gates. So I've put in some examples, but I just leave them to you so you can just take a look at them. In case you want to convince yourself, I have a worked 3-qubit case. And the examples which you will find now hopefully can give you some additional intuition here. So the inverse is actually important because this is, well, if we just look at this, the phase encoding is what makes the QFT so useful in the phase estimation algorithm, which we're going to look at. In case you want to implement Shor's algorithm, you actually need to deal with period finding. And the thing we are going to look at is actually to extract the eigenphases and eigenvalues. So QFT converts arithmetic structure into measurable interference structure. And the inverse is obtained by reversing the circuit and taking Hermitian conjugates. So in the quantum phase estimation algorithm, what is central is actually the inverse quantum Fourier transform. And I'm going to show you how that pops up. So you will simply replace that by Hermitian conjugate to reverse the order of the gates and keep the same swap network. So many algorithms actually use the inverse rather than the forward quantum Fourier transform. So this is the count which I wanted to bring up before we move on. So I promised that one. So if we have n qubits, you see now that we will roughly have n Hadamard gates. We're going to have n times n minus 1 divided by 2 control phase gates. And then we have this swap gates. If you leave out the swap gates, you see simply that what you will have is n times n minus 1 here. So that means that the total gate count is roughly n squared. So if we go back to this simple estimate, which we had before the break, so this is exponentially more efficient than applying the classical DFT. So the latter requires n squared. So if you plug in with just 3 qubits, you have 9 versus 64 operations, roughly. So already with 3 qubits. And with 100 qubits, you have 10 to the 4, compared with 2 to the power of 200, which is 10 to the 60. So this is also something, if you're interested, as a project tool to compare fast Fourier transforms, discrete Fourier transforms with quantum Fourier transforms, and look at speedups and apply these to a real quantum computer. That's also a possible path for project two. Now, I hope I'm not giving too many options here. But when you have these tools, quantum phase estimation, quantum Fourier transform, and the VQE, there are many, many interesting things which we can do. Now, there's something which is also called an approximate QFT. When you have a small angle phase gates, they normally just don't contribute much, and that can give fewer gates and a shallower circuit. And this is often what we are looking after. So people have used machine learning to optimize the length of a quantum circuit. That's another interesting topic, which we will not cover by obvious reasons. I mean, there's a limit to how much we can put into 10 credits. So a typical implementation, so you choose a number of qubits, you loop over the qubits, you apply H on qubit J, each later qubit K larger than J, you apply a control swap, and at the end you reverse the qubit. And this is actually what we have. This kind of logic is the one which is implemented in these notebooks here. So take a look at them for implementations. So in case you want to implement the QFT and the QPE, then clearly take a look at these codes actually. Yeah, I'm going to leave out some of these things here, and then what I wanted to say something about is the quantum phase transformation algorithm. And if we just look at the summary here, there's a quantum analog of the discrete Fourier transform. It acts as an operation on a given state. It factorizes into one qubit phase states, is implemented using Hadamard's controlled phase gates and swap gates, and has this complexity. And it's central to phase estimation and many other algorithms. So if you are interested in applying this HH algorithm, which solves linear equations, then you need both the quantum Fourier transform and the quantum phase estimation. So I wanted to start with the quantum phase estimation and say something about this, and we will probably need some time after the break as well. So suppose now that you have a unitary operator, and phi is one of its eigenstates. And we know that if we have a unitary operation, this is given by some angle phi here, where phi lives between 0 and 1. So the goal of this quantum phase estimation is actually to find this phase phi. And if you are interested in eigenvalues, so the QPE, this is actually the quantum phase estimation algorithm. So it's a way to estimate that phase. So equivalently, the QPE extracts the eigenvalue of U in a phase form. So we're going to see quickly how this actually comes into play. And it was the basic first algorithm which was used to find eigenvalues of Hamiltonians. So it's been used as an energy estimation. The problem is that the circuits are pretty long, but the eigenvalue problems in many body physics is something which this has been applied to. Hamiltonian simulations, Shor's algorithm. It's essential in the linear algebra variant, this HHL algorithm, which I mentioned earlier. So if you can encode the Hamiltonian into unitary, then the QPE can extract its eigenvalues. So we're going to see how we can do that, okay? So it uses two registers. So sorry, but I'm going to use these slides. So there's a control register of n qubits, which are then initialized typically as a tensor product of zeros. So this notation which you see here, you have n qubits, and then this is initialized. And then you have a system register, which is initialized in a state psi. So the initial state of the system is actually the tensor product of these two states. So the idea then is that this control register stores the estimated phase bits. So let's see how that takes place. Okay, any questions so far? So if you then, so when you create a, the first thing you do is to create a uniform superposition. So the states are not entangled, keep that in mind. This is just a uniform superposition of Hadamard's. So that means that, and remember now that these K states, which we have here, are then multi-qubit states. And this can be broken down into K1, K2, K3, and so on, where each of the smaller K values take only values 0 and 1. So the total state then, and I'm skipping the tensor products here, can then be written as this states where we apply the Hadamard, and this prepares the control register as a coherent superposition of all binary numbers K. So this is a superposition of all the qubits which we have accessible here. There is no entanglement between these qubits when you do a Hadamard. Keep that in mind. Then you apply the control powers of this operator U, and each control qubit determines whether the corresponding power is applied. So because phi is an eigenstate of this one, then this turns into, since this is an eigenstate, keep that in mind, we have assumed that psi is an eigenstate of this unitary transformation. Then we can actually rewrite it like this. And this means that each controlled unitary writes phase information into the control register. So if the control register basis state is K, then the controlled operations give us this. And that means that the combined state becomes something which is look alike of the quantum Fourier transform, because this factor which we have here is essentially what we also had in the Fourier transform. When you have that, so what you see now is that the system register factors out, which is this one, and the control register now contains the phase information. This is the control register. And the control register is in this specific state, which is a Fourier type state. And this is why when you do the inverse quantum Fourier transform is a correct next step. It converts the phase encoded superposition into a computational basis approximation of phi. So if I do it, if you look at this one, this is just a state which I've transformed. If I perform the inverse Fourier transform, I can get the information phi. That's the basic idea here. So when you apply the inverse Fourier transform to that control register, this one, so if this phi is then given by some integer m divided by 2 to the power of n, then this simply becomes the state n. So the control register can store the exact n-bit binary expansion of this state phi. So if you take, suppose you take this one, and this is given by m divided by 2 to the power of n, then the inverse QFT, then when you apply that one, the control register simply becomes phi 1, phi 2, phi n. And then you can extract the binary float, which represents this number phi, which is a number between 0 and 1. So when you measure the control register, that returns the exact binary digits of phi. And this is the cleanest case of a QPE. So if you now look at the step-by-step derivation, so suppose this phi is given by this representation. So if you can represent exactly phi in a binary float, then you can actually extract the exact phi. So then you can show that the control register state after control power factorizes like this. And then because you have this relation here, which is now given by if you multiply with 2n minus 1, then only the fractional parts matter in the phases. So each qubit encodes one successive binary suffix. So using the binary expansion, the control register state, and you see that this is exactly the structure of a quantum Fourier transform, and applying the inverse quantum Fourier transform yields the bit string which we are interested in. So that means that what you're going to do then, you perform this set of Hadamard operations. You have this unitary operations on the different qubits together with the register, which you have here. Then you perform an inverse Fourier transform. And then at the end, you perform the measurement on the different qubits. So suppose now phi is equal to 5 divided by 8. That means that you have an exact binary float representation. Then the ideal QP output on a 3-qubit control register is actually 101. And indeed, if you take this one, this is actually given if you take phi. So phi is now given by 5 divided by 8. So after the control powers and inverse QFT, the control register collapses to the bit string 101 with probability 1 when you perform the measurements. So if it's not exactly of this form, then the QP does not return one exact bit string. So that's a problem we have to face with the QP, because given finite number of bits cannot represent exactly all floating point numbers, can only approximate them. So when you do these n-control qubits, that resolves phases to approximately this correction here. So the precision improves exponentially with the number of control qubits. But the more qubits you have, the deeper the circuit and the longer the circuit. So the more precision you want, the more qubits you need. And that's one of the drawbacks of the QPE. So you can also calculate the eigenenergies. So if you have a Hamiltonian with eigenstate E, so these are the eigenenergies E, then you would define the time evolution operator like this. And then what you have when you act on this state is that this simply is given by the exponential with the energy times this state. And when you compare what we did previously with the phase estimation algorithm, you can identify the phase as E times T divided by 2 times pi. So if you can implement E to the minus I times H times T, then you can estimate the energies. Yeah? Not?
Why didn't we write 1 after?
Oh no, that's a typo actually. Yeah. No, that's you don't need that one. Sorry. Yeah. Sorry, that's a typo. Yeah, I see that. So when you connect this to Hamiltonian simulations, you have requires a controlled applications of these operations here. So it depends directly on the ability to perform Hamiltonian simulations. So in practice, this is done by something which is called Trotter-Suzuki decomposition, which we will discuss a little bit more after the break, because we are going to mention the QAOA algorithm, the quantum approximation optimization algorithm, and that needs the trotterization. So what I'm dropping many of these ideas to you now, and then we will pick this up after the break and look in more detail at codes, etc. So the QPE measures the dynamical phase accumulated by an energy estimate and the time evolution. And the algorithm turns the phase into a bit string encoding the energy. So you can view the QPE as a highly precise way to perform energy measurements. It's important in, for instance, quantum chemistry and many-body physics is often to compute eigenenergies. So you can use that to look at ground state energies, excited state energies, spectral properties. Connection to the VQE. The VQE, if you now look at it, there are some things to which we can discuss a little bit more in detail after the break. So the VQE is variational. It's a hybrid quantum classical, and it's optimized by minimizing, and it's suitable for actually noisy devices. The QPE is not variational. It requires coherent control time evolution. It provides a direct eigenvalue estimation, and it's normally suited to fault-tolerant quantum computers because it gives very lengthy circuits. So the QPE, they can actually complement each other. And this is a possible path for the second project. So you can use a variational method such as the VQE to prepare a good eigenstate. with large overlap with a true eigenstate. And you've seen that the VQE gives a pretty good estimate. And then you use that state as an input to the QPE. That's when you start the simulation with the Hamiltonian, because you have a time evolution. So you have a trial state. And because in the QPE, what you're doing is actually to act with this operator on H. And you have to trotterize actually to write out the exponential of the Hamiltonian. But then the QPE can then be used to refine the energy estimate to high precision. So you can think of the VQE as a way to prepare the initial state, which is then taken over by the QPE. So this is another path for the second project. I'm going to skip some of these things, but I wanted to say something. Let me just skip this one. I wanted to say something about the second project, and then we stop. Sorry. So here I have several ideas, and I want you guys to think of these during the break. If you have some clear ideas of what you want to do, please send me suggestions. You don't need to write a long suggestion, be half a page or something like that, for what you want to do. But here I actually have several things which I'm going to wrap up as possible paths of project 2. So one is a continuation of project 1 with more realistic systems and where you actually run on real quantum computers. So that is a well-defined project which picks up what you've been doing. And Qiskit has links to realistic Hamiltonians, which are used in quantum chemistry simulations. Now, one of the things which I'm quite interested in is, and which we will discuss after the break, is the quantum approximate optimization algorithm, which is in a way follows up from what we've been discussing before. We also have the HHL algorithm, which needs the QPE, and which then can be used to simulate linear algebra problems on quantum computers. We're also going to discuss quantum machine learning algorithms after we have discussed the QAOA and the HHL. You can, if you want to implement the quantum neural networks, that is possible. And we will discuss that after the break. So that would be in the second half of April. There are many other ones. Implementing Shor's algorithm is something which I normally recommend if you have a good familiarity with number theory. Some of you may be more interested in the possibility to parallelize variational quantum eigensolver with multi-GPU scaling. There's an interesting paper here, and they actually provide a lot of details. So if you're more into the computational gate, I mean, this is a useful algorithm. You can implement and compare the quantum phase estimation algorithm with VQE. And there's a recent paper which actually evaluates the QPE against the VQE. So that is a nice calculation. We have studies of hyperparameters in VQE. This is another paper which pretty recent, because when you do the VQE, it's an optimization problem. And the studies of the hyperparameters, so this will be a more numerical study. If somebody's interested in copper cluster theory, there's a unitary copper cluster. That's also an interesting project. So just quickly of what the QAOA stands for. And this is where we will, so after the break, I'm going to try to wrap up this QPE discussion. And then we will use at least 2 sets of lectures on the QAO. So it's you can see what it stands for. It's a variational quantum algorithm. So I said that a kind of keyword for this course is variational quantum algorithms and parameterized quantum circuits. There's a kind of common denominator for what we are doing. And then you have many famous algorithms. So the QAOA is actually widely used in optimization problems. And it's a parameterized quantum circuit. It's a variational quantum algorithm that uses a parameterized quantum circuit to search for good solutions to hard optimization problems. Now, the other algorithm, which we will also discuss after the break, And this is named after these three persons, and one of them is in disgrace nowadays. And this is a central algorithm, and the core idea is actually to solve these equations, which is essential if you do differential equations or just interest in linear algebra. So these are the things which we will discuss right after the break, together with a summary of the QPE and discussion of how we implement the QPE. And then during the break, just think a little bit about what you would like to do. I'm going to make proposals based on those different suggestions, but some of you have already pretty well-defined topics you want to study. So this is something you can see as a continuation of what we've been doing. And we are going to look at parameterized quantum circuits with optimization, because we have sets of parameters we want to optimize. And when you do neural networks or any of the machine learning algorithms, you're actually going to have a parameterized quantum circuits where the parameters of the neural networks are actually the rotation phases in the gates. Okay. So this is roughly an outline of what we're going to do the rest of the semester. And the choice here is simply due to the fact that these are central algorithms, which you will encounter when you look at quantum computing algorithms. Okay, so happy holidays when they come. Enjoy your break, well deserved. Thanks for heroic efforts with the first project. And we are planning to come with a feedback right after the break. Hey, enjoy.